Okay, welcome to topic 1.7, periodic trends. For the essential knowledge, we will be looking at the organization of the periodic table and how it is based on the recurring properties of elements and explained by a pattern of electron configurations in the presence of completely or partially filled shells and subshells of electrons in atoms. So when writing the electron configuration, please note that elements that are exceptions to the Aufbau principle will not be assessed on the AP exam. The rationale for it, the mere rote recall of the exceptions does not match the goals of the curriculum revision. Another one that we're going to focus on in these notes is that trends in atomic properties within the periodic table, or periodicity, can be qualitatively understood through the position of the elements in the periodic table, Coulomb's law, the shell model, and the concept of shielding or effective nuclear charge. These properties include ionization energy, atomic and ionic radii, electron affinity, and electronegativity. And we are going to discuss how electron affinity and electronegativity are different. The periodicity, mentioned prior, is useful to predict and estimate values of properties in the absence of data. So here we go with some notes. So the periodic table is arranged in order from lowest atomic number, or number of protons, to the highest. The blocks of the periodic table correspond to the SPDF groups for electron configuration, which we discussed in the previous thing, but did not draw it down. But here you have it wonderfully laid out for you. The elements that have the same valence electrons tend to have similar chemical properties. Okay? I want you guys to remember that when you are discussing periodic trends or anything related to electrons, you should always explain why using Coulomb's law and not say because of Coulomb's law. You want to state why based off of the strength of attractive and or repulsive forces. So remember that electrons are attracted to the nucleus. You want to discuss that. Or why two electrons repelling each other in the same orbital might cause slight fluctuations in binding energy. Hint, that actually is, I think, a practice question. Okay. Moving on, most, if not all, periodic trends can be explained by the arrangement of electrons and the number of protons in the atoms. Okay, remember, stating a trend is not explaining the trend. Explanations of trends should never be in terms of the location of the periodic table. You need to discuss it based off of the arrangement and how that contributes to the strength of the attractive force. So Coulombic attraction is the electrostatic attraction between two charged particles, and it is missed some stuff. Electrostatic attraction between two charged particles, electrons and protons in the case of the atom. Often when discussing periodic trends, the charged particles are the nucleus, specifically the number of protons, and the electrons. Often we are referring to the outermost electrons, which are the valence electrons. So Coulomb's law states that the attraction between two charged particles is proportional to the magnitude of the charge and inversely proportional to the distance between them. We have stated this before in previous sections, but we're going to keep reiterating it because this is a very key point. Make sure you understand this, okay? To make this simpler, the larger the charge, the more attractive force between the particles. The further away the particles are from each other, that force then becomes weaker. Periodic trends, we're going to discuss them. So we're going to discuss them in terms of Coulombic attraction and electrostatic interactions. So these are the positive negative attractions which take place when you have two charged particles in close proximity. And we have discussed that this increases with an increase in charge and it increases with a decrease in the distance. So that's the inverse relationship. Okay, how does effective nuclear charge work with this? Effective nuclear charge is the net positive charge experienced by valence electrons, and it's approximated by this equation, where Z is the atomic number and S is the number of electrons in orbitals that are closer to the nucleus. So we're going to use these two concepts to now discuss periodic trends. So the first is ionization energy. This is the energy required to remove the outermost or highest energy electron from the gas of a neutral atom in its ground state. The first ionization energy decreases as you move down a group. This is because electrons are further from the nucleus and therefore have lower Coulombic attraction. Additionally, inner shells of electrons shield or block the proton force of attraction so that the outermost electrons do not feel as much of the nuclear force. This results in outer electrons being even easier to remove. The first ionization energy increases as you move across a period on the periodic table from left to right. As you move across the period, the atomic radius is smaller and there is an increase in protons in the nucleus. Okay? Both factors result in a greater Coulombic attraction. You want to focus on the protons as you go across the period, though, because that is the one that is increasing more, like, in greater proportion. The radius doesn't change as much, like, as drastically as the charge does. It's there, it's fine to argue it, but across a period, you're going to want to make sure you're focusing on the increase in protons and thus increase in great Coulombic attraction, which means that it will require more energy to remove that first electron. There are a few places where the ionization energy does not appear to follow a trend. You can see this on the graph between beryllium and boron or between nitrogen and oxygen. This is for slightly different reasons. The beryllium and boron exception, when the first electron is removed from the boron atom, the electron is being removed from the 2p orbital. Since the 2p orbital is further away from the nucleus, it's going to take less energy. Okay? So that kind of breaks that slight trend. That's why you see a slight dip. The N and the O exception, when you first see the electron removed from oxygen, it's requiring less energy despite the increase in protons than compared to nitrogen, because the electrons in oxygen are sharing the 2px orbital and they have greater electron-electron repulsion, so one electron is trying to kick the other electron out of bed or out of its orbital. Okay, that makes it easier to remove that electron. So increasing that electron-to-electron repulsion decreases the proton-to-electron attraction. So the second ionization energy is the energy to remove a second electron from the atom, and so on and so on. So by examining the successive ionization energies, so that means how much energy is required to remove each one as you go through, you are able to determine how many valence electrons there are. When all of the valence electrons have been removed, you will see a large jump in the ionization energies. And when we look, we see that going here, right? That is a very large jump of about 6,000, and it doesn't get much bigger than that until we get much further down, like here. Okay? So that tells us, right? So this jump is due to the fact that the core electrons are closer and less shielded from the nucleus, and thus these are going to require more energy, as it's showing. So that means that these are core electrons. That tells us that these first two are our valence electrons. So for example, consider magnesium, where the electron configuration is given, and we see that it has 2 valence electrons. You can see that there's a big jump, and this is for magnesium here. There's a big jump going from the second to the third ionization energies, and again between the 10th and the 11th. This shows when electrons are being removed from a shell that is closer to the nucleus. So this is our second shell, and this is our first one. So that's why it's even closer, so it's going to require even more energy. Okay, moving on. Atomic radius. The atomic radius of a chemical element is a measure of the size of the atoms, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding cloud of electrons. The atomic radius increases as you go down a column as there are more electron shells. It decreases as you move across a period on the periodic table. This is because electrons, sorry, I have to change my page. This is because electrons are being added to the same energy level. At the same time, protons are being added to the nucleus. So the distance is increasing, but you're increasing the effective charge, right? So it has a higher effective nuclear charge. In other words, there is a stronger force of attraction pulling the electrons closer to the nucleus as you go left to right. This results in a smaller atomic radius with greater numbers of protons. There's a greater pull on those electrons. Ionic radius is the trend. The trend for ionic radius is similar to those of ionic atomic radii, except that cations and anions are going to be discussed separately from each other. Like, you can't really compare the two because one's losing, one's gaining. So cations are always smaller than their parent atoms because they've lost their valence shell electrons. Okay? This causes them to be smaller. They also decrease in size because the nuclear attraction is now acting on fewer electrons. So they are drawn in toward the nucleus due to a greater attraction. Anions, on the other hand, are always larger than the parent atom. That is because electrons are added to the same valence shell. However, there are greater electron-electron repulsions, so the ion increases in size. Okay? And we see an example in this image to the right. Next, we have electron affinity. This is related or similar-ish to electronegativity, but there's a distinction. Electron affinity is the amount of energy involved when an electron is accepted by a gaseous atom to form a negative ion. Okay, so its ability to accept an electron, like take it into itself. In other words, the neutral atom's likelihood of gaining an electron. So can it become an anion? The values tend to be negative to show the energy is released as electrons are added to atoms. In general, electron affinity increases left to right on the periodic table. This is caused by filling of the shell of atoms. Group 17 atoms release more energy than group 1 atoms when they gain an electron. This indicates that it's more stable. A trend of decreasing electron affinity when moving down a group in the periodic table is expected. The additional electron will be entering an orbital further away from the nucleus. Since this attraction is further from the nucleus, it is less attracted to the nucleus and releases less energy, so lower Coulombic force. However, a counterexample is found in group 2, and when you expect the periodic table that this tends to only apply to group 1 atoms. Okay. So this one is a little tricky to test on, but it's good to know. Electronegativity does have clearer boundaries and predictable trends because of fewer exception rules. And remember at the start we said that exception rules are not tested. So electronegativity is a measure of the ability of an atom to attract shared electrons. So this electronegativity decreases as you move down a column because of a greater distance from the nucleus and because you have electron shielding. Okay, electronegativity increases as you move across a period on the periodic table. This is because the atomic radius is decreasing, while the number of protons or effective nuclear charge is increasing. You want to focus on the charge increasing though, because that is the most dramatic effect. Okay, so just remember that electron affinity, discussed prior, is ability to become an anion. Electronegativity is it's a pull on a bond or a shared pair of electrons. Okay, so one's for ions, the previous one. This one's for bonds, like chemical covalent bonds. Okay, next we are going to do our I do's and we do's and conclude these notes. For each of the following elements, so we have sodium and lithium and oxygen and fluorine, we're going to choose from each pair the one with the higher ionization energy, larger atomic radius, and higher electronegativity. So when we look at this, highest first ionization energy out of sodium and lithium is going to be lithium, because it is closest to the nucleus. So it's going to experience a higher attractive force, so be harder to pull off. Out of fluorine and oxygen, it will be fluorine has the highest first ionization energy out of the two, because fluorine has a greater force of attraction. So the effective nuclear charge is greater than oxygen for fluorine, because it has 9 protons versus oxygen's 8. For B, sodium versus oxygen, no, not sodium, that's the answer. Sodium and lithium, sodium is going to be bigger because it has an additional ring of electrons. Like it's got 3 energy levels, 3 shells with electrons versus lithium's 2. Fluorine versus oxygen, it is going to be oxygen because its valence electrons are less tightly held, allowing them to be bigger. Okay, because of a lower attractive force from the nucleus. Then finally C, higher electronegativity, sodium versus lithium. That is going to be lithium because the electrons are closer to the nucleus, and thus it's able to attract better. Sodium and lithium, I said that. Okay, next is fluorine and oxygen. It will be fluorine because fluorine has a higher effective nuclear charge, so it is better able to pull in those electrons to itself, thus having a higher electronegativity because of greater effective nuclear charge. Okay. Next, our we do's. Rank the following from the smallest to the largest atomic ionic radius. Okay, so we can kind of do this together. So for the first one, A, we'll do that one together and then I'll let you do the others because ions are kind of tricky. So when we look at A, we know the one that has to be in the middle between the two is the one that hasn't changed, which is sodium. Okay, and we want to rank it from smallest to largest. So the smallest one will go first, which will be the one that loses an electron, which is sodium with a 1+ charge. It's going to be smaller than sodium, neutral atom, which should be smaller than the ion that has gained an electron and thus added more to its electron cloud and thus increased in size due to increase in electron-electron repulsion. Okay, pause the video and complete B through C, and then we will check back in and I will explain why. Okay, so for B, we put O, C, then O, and then C, because oxygen should have the greatest effective nuclear charge, so pull its electrons in most tightly, so it should be the smallest, whereas carbon has the lowest effective nuclear charge and not pull them in as tightly, so it should be the largest. Okay, for C, these are all in the same period, so we're going to look at, so as a hint, if we're looking at a period, so elements that are in the same period, we're going to focus on the effective I can't spell, nuclear charge. And if they are in the same group, you're going to focus on the electron shells, which is your distance. And then relate that to Coulomb's law to justify the trend. Okay, so for C, those are all in the same period. So we're going to look at the effective nuclear charge. So argon has the highest effective nuclear charge, so it will be the smallest because its electrons are pulled in the tightest. Chlorine would be next because it's got an effective nuclear charge of 7 versus argon's 8, so not pulled quite as tight, versus potassium, which has an effective nuclear charge. Oh. Those are in different groups. Potassium should be bigger, I think. I think potassium goes here. My bad, guys. Sorry. I thought I knew what I was doing. That's a little weird that they aren't all in the same. So potassium, because it's got an effective nuclear charge. Oh, it should be bigger. It's in the right spot. Miss Bert's just tripping. So it should be bigger anyways because it's in the next group, right? So it's got more electron shells. That next energy level should be even further away than argon or chlorine. Okay, so it should be bigger. Then looking at D, these are all in the same group. So I'm going to focus on energy shells, which then relates to distance. So beryllium has 2 energy shells, magnesium 3, calcium 4. So they should be ranked beryllium as the smallest, magnesium as the middle, and calcium as the largest. Thank you, guys. Complete the you-dos for practice so you can check your work in class, and thank you for tuning in.